So I'm very glad to welcome Evgeny Feigin from the High School of Economics and announce his talk on Quiver Grassmannians and Grassmannian necklaces.
Thank you very much, and thank you very much for the invitation. It's a pleasure to talk here. Well, although I'm talking in Zoom, but well, at least there is some way to talk. And since the talk is online, so please ask as many questions as possible. So please interrupt me at any point. Your comments, remarks, questions are very welcome. Well, let me say from the very beginning that this is based on the joint work with Martino Lanini and Alex Putz. And well, here is a brief plan of the talk. So I'll start with an overview, just a brief description of what's going to happen. And then I'll say a few words. Well, I'll give basic definitions about Quiver Grassmannians. Then I'll pass to the case, which is especially interesting for me. So this is the case of cyclic quivers. Well, I'll introduce the main object we're going to work with. When I'll pass to the combinatorics and geometry, so the main combinatorial object going to be Grassmann necklace, and then I'll give the definition, and then I'll explain why it's important for the study of the geometry of the varieties I'm interested in. Finally, I'll say something about totally non-negative Grassmannians. This was actually the starting point of the whole project. Although, well, I'm not going to give much details here just because of the time, but anyway, I'll say something. So let me start from the very beginning. The idea, or rather the initial point, was the Postnikov construction of the so-called non-negative Grassmannians. So I'll give the precise definition at the end of the talk, probably. But important thing is that this is something, and this something has nice combinatorial and geometrical properties, and the combinatorial properties, as well as some part of the geometry, are governed by the so-called Grassmann necklaces. So this is the, well, in short, so these are collections I1, IN of subsets of the set from 1 to n. So they have to satisfy certain conditions. These are Grassmann necklaces. And then, so the non-negative Grassmannian is defined over R, so it's important. And then it turned out that those Grassmann necklaces, they are very kind of natural for the study of certain complex objects, which are Quiver Grassmannians. Quiver Grassmannians for cyclic quiver, so delta n, just a quiver, well, one consisting of one cycle. Again, I'll give all the definitions. And this is kind of turned out that, so this is over C. So it turned out that the real geometry of the Postnikov's totally non-negative Grassmannians, well, is related to the complex geometry of those algebraic varieties, and this connection is interesting and allows to derive certain properties and certain nice features of both sides. So I'll concentrate today on the Quiver Grassmannians, and then at the end I'll get back to the Postnikov's construction and I'll explain what is the connection. So this is the overview. So now let me get to the explicit definitions. Quiver Q. So this is the data consisting of the set of vertices and the set of arrows. And well, the arrows, they have the starting and the target. So the starting vertex and the targeting vertex. So say let me take two vertices I and J, and so I have an arrow between the two vertices. And I say that I is the starting point of alpha, and J is the target of alpha. Well, this is very kind of standard definitions. So these I and J are vertices, and alpha is an arrow. So this is my quiver. Well, in principle, for me, Q0 is always finite, Q1 is always finite, but you might be interested in some examples where some of the sets are both are infinite, but this is not the case for the today talk. Okay, so this is the Quiver, and now I need a representation of the quiver. And again, so this is a very natural thing. So one attaches a vector space. So let me denote it by mi. So this is so I is a vertex. So this is a vector space attached to I. And also I have maps M alpha from ms of alpha to mt of alpha. So these are linear maps between the vertex, between the vector spaces corresponding to the vertices. So that's it. So a representation of Q is just a collection of vector spaces attached to vertices and collection of linear maps attached to the arrows. Okay, so well, let me denote by M this data. So I from Q0 and alpha from good. Now let me give you an example. Well, the example, probably the simplest one. So let Q be just what is called equivarianted type A quiver. So meaning that you have n vertices and you have arrows between the vertices. So well, we have to consider vector spaces attached to the vertices. Let me just take some vector space V. And let me take all the maps to be just identity maps. And this is an example of a representation, so probably a bit boring, but still this is a representation. Okay, so now, well, there is a notion of sub-representation. So this is n inside M, meaning that we fix ni inside mi for any I. And the condition is that alpha of ni sits in nj for any alpha from I to J. So this is a sub-representation. And well, definitely there is a notion of direct sum of two representations. So double tilde of direct sum. Well, you just take direct sum of all vector spaces and direct sum of the corresponding mappings. So, well, this is very, very kind of standard and very natural. Okay, and so in particular, M is called indecomposable if you can decompose it into the sum of two. For non-trivial M tilde and M double tilde. Okay, so now maybe slightly less standard object is a Quiver Grassmannian. Well, maybe this is already the no, this is still the first part. Okay, so what is a Quiver Grassmannian? So we take gr, and then we take the dimension vector E and representation M. Here, E is a collection of EI I from Q0. So this is what is called the dimension vector. So this is an element in Z greater than 0 to Q0. So for each vertex, you take a number. And well, M is a module. And then by definition, so this, so we denote this, just put it brackets. And then this Quiver Grassmannian, this is the variety consisting of submodules n inside M such that the dimension of n is E. So maybe I should have said above that the dimension of a representation is just a collection of dimensions of the vector spaces attached to the vertices. So we consider all submodules inside a fixed module such that the dimension of the corresponding submodules is fixed by our EI. So for sure, the EIs have to be no larger than the dimensions of the MIs. Otherwise, we have no chance. But otherwise, this is something. And let me give you some examples. Well, there are some trivial examples, and the most trivial is Q is just one vertex, no arrows, just a very simple thing. And well, M is then just a vector space M1. And well, E is a vector, is a number. The dimension vector E is just a number. And then the Quiver Grassmannian of M is nothing but the, well, just the Grassmannian of E-dimensional subspaces in the dim M dimensional space, M1. Okay, so a bit less trivial example, but still very standard, is Q being the equioriented type AN Quiver. And M is a representation we've seen above. So we have V and the identity maps everywhere. And so let E be, well, maybe even to make it even more precise. So let me assume that we have here n vertices. And let me assume that dimension of V is n+1. And I take E to be just 1, 2, up to n. And then clearly, the Quiver Grassmannian is nothing but the flag variety. Flag variety for SLN+1. Okay. So just because what we have to do, we have to fix one-dimensional space in the first V, two-dimensional space in the second V, up to the n-dimensional space in the last V, and they have to be embedded into each other. This is exactly the definition of the flag variety for type A. Let me show you that the Grassmannians, the Quiver Grassmannians, in general are very complicated. So, well, still not too complicated, but a bit more interesting example is as follows. So let Q be A2 Quiver. So two vertices, one arrow within the vertices. And let me take M to be a two-dimensional space at the first vertex, a two-dimensional space at the second vertex, and well, a map between those, just the rank 1 map. So you can consider it as given by the matrix 0, 0, 0, 1. And I take E to be 1, 1. So I'm looking at a one-dimensional subspace at the first two-dimensional K2, and then a one-dimensional the second two-dimensional K2. And then they have to be related by this simple map. And what is this? Actually, you can easily see that this Grassmannian is a one-dimensional variety, which has two irreducible components, and they both are isomorphic to P1. And this P1 have one common point. So let me draw the picture. So I have one P1 and another P1. So this is a complex picture. So say K is C. And we have two P1s sharing one point. So in particular, we can see even in this simple example that the varieties do not have to be irreducible. They can have as many irreducible components as you wish. But even worse, it can be disconnected. So again, we can consider example of a quiver with two vertices. But now let me take two maps within these two vertices. So such a quiver is called the Kronecker quiver. So this is my Q. And now my M is going to be, again, a two-dimensional space. The first vertex and the two-dimensional space at the second vertex. But now I need two maps between the two vertices, between the two vector spaces. And the two maps are given by the identity for the first one and by the same map as we had before. So let me also consider the same dimension vector. So you can see I am choosing very simple and naive data, but even here, what you get is E of M is just the variety consisting of 2 points. Well, simply because, so since the map is the identity, one of the maps is the identity. If you have a one-dimensional subspace in the first vertex, then you are urged to take the same one-dimensional space in the second vertex, but then you have the second map, 0, 0, 0, 1, and you take invariant subspaces with respect to this map, and there are two invariant subspaces, and these are the 2 points we're looking for. So you can see that the question of how many connected components, how many reducible components, what the dimension of the variety. So these are very reasonable questions. And in each particular case, they have to be answered by, well, some tools. So this is not at all evident. Okay, probably that's all I wanted to say about the basics on Quiver Grassmannians and Quiver representations. So any questions so far? Okay, so if not, let me go further. And so for me, for today, the most interesting, well, actually the only Quiver I'm going to be interested in is the cycle. So let the cycle on n vertices. So this means that we have to add that the arrows are pointing in one direction. Again, so we can choose whatever we want, but for today, I'm only considering the Quiver of this sort. So this is my delta n, and we have a lot of representations of this Quiver. So delta n module is a collection of vector spaces mi. So I from 1 to n. So it's a vector spaces. And also we have mappings mi to I plus 1 for I from 1 to n. So these are maps. So please note that if I is n, then this map is a map from nth vertex to the first vertex. So since this is a cycle, so we have no problem with moving along it. And the representations we are going to work with, they are, okay, maybe before I go further, let me give you an example again. This example is going to be important for us. So assume M isomorphic, or just given by Cn. So we have n-dimensional complex vector space allocated at each vertex, and all the mappings I to I plus 1, or let me put M here, it's going to be just the identity map. Then if I take the Quiver Grassmannian given by the dimensional vector k, 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 so the same number for each vertex of this M, then this, again, very simple thing. This is just the Grassmannian of k-dimensional subspaces in an n-dimensional space, since all the mappings are the identity maps. But this is, of course, a bit boring, but the object I'm going to work this with is also Quiver Grassmannian for the same dimension vector, but for a different representation M. So let me give you a definition. So let me define UIN to be, this is the delta n module, such that the dimension of UIN at any vertex is just 1. Yes, so for each vertex we attach a one-dimensional vector space. So we also have to add maps. So let us also define we set alpha I plus 1 to be 0, and alpha j plus 1 is the identity for j being not I. Okay, so well, these are our maps, and since all the spaces are one-dimensional, so we either have the identity maps or the 0, and so let me draw the picture. So this is going to be an important thing. So for let n be 3, I is 1. So then our quiver has 3 vertices. 1, 2, 3. So we have 3 vertices, and at each vertex we have a one-dimensional space, C, and C. And I want to consider this space, the representation U, say 2, 3. So 3 is my n, and oh, I took 1, sorry. So how does it look like? So we have a map from 2 to 3, this is the identity map. We have a map from 3 to 1, this is the identity map. And we have nothing here. So of course we have such an arrow, but the corresponding map is 0. So well, again, this is a very simple representation. However, this is different from just being totally identities everywhere. And so remark, each UIN is nilpotent. So meaning that well, if you take the concatenation of several arrows, yes, then you get 0. So in other words, the composition of any n consecutive arrows is 0. So we can clearly see this on the example. If you take 3 maps, one of them is going to be just trivial, so that's fine. Okay, and now the representation I'm going to work with is UN. So it's just a notation, and by definition, this is the direct sum of UIN, U from 1 to 1. Okay, so I take all the simple, well, I mean, all the representations of the form UIN, and I sum them up for all I from 1 to n. So they are all here. So in particular, the dimension of UN is n. So they are summed up to n-dimensional subspaces, n-dimensional spaces at each vertex, since the dimension of each UIN is 1, and we have at each vertex again, and we have n summons of this sort. So again, let me give you an example. So if n is 2, then well, we have U2, And this U2 is, again, very simple thing. So our quiver has two vertices. So the first and the second vertex. And we have two arrows between these two vertices. One arrow is pointing in one direction, and another arrow is pointing in another direction. So this is my Q. The Q is just delta 2. And this is the quiver, and we need representation. So the presentation is C2 at each vertex. And I need two maps between this C2, one in one direction, another in another direction. And so let me give you a picture. So I draw process for vectors in each of the C2. So at each vertex, I have a two-dimensional space, and therefore I have two crosses for the first vertex, two crosses for the second. And well, the mappings are here and backwards. So maybe I even choose another color. So maybe I'll use green and blue. And then for second map, I need the green one. So, well, you can see that both maps are rank 1. They are both maps from C2 to C2. Okay, so now the main definition, the main player is the variety, which I denote by xkn. So by definition, this is the Quiver Grassmannian for dimensional vector k, k, k inside UN for some k from 1 to n minus 1. So this is a collection of varieties. So there are n minus 1 of them. And so this collection depends on both parameters. And so just to give you a feeling, so let me again consider example.
Can you recall who is UN?
Yes, sure. The UN is the direct sum of UIN. So this is a representation, which is the direct sum of n representations UIN. All of them are one-dimensional at each vertex, and the total thing is n-dimensional. So we consider inside this UN sub-representations of dimension k, 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 k at each vertex.
So UIN, what are the morphisms?
So for yes,
like this.
Yes, so you can see so that UIN is one-dimensional space at each vertex, and then the morphisms are either identities or zero, and there is only one zero map from I to I plus 1. All the other mappings are identities. And then you sum up.
Sum them all, so in each place there's only one thing that you do 0, yes?
Absolutely, yes. So at each place, at each vertex, you have one-dimensional kernel. That's true. Mm-hmm. So the simplest example is case 1 and n is 2. Well, we have the corresponding representation in the example above, and we need one-dimensional subspace here and there. So need a one-dimensional here and the one-dimensional here, such that the maps, which we do have, they map one guy to another and another to the first one. So, well, the claim is that here the x12 is, well, it's the thing we've already seen. So this is two p1s glued at one vertex at one point. So this is my x12. And well, it's easy to see that this is indeed the case, because if you take the, so let me again choose some color. So if you take this two-dimensional space and you choose a one-dimensional space there, so if you have this vector corresponding to this red circled cross, then the right-hand side is just, well, determined. Even more if you have, let me do it vice versa. So if you have this vector, then you have no conditions for the right one-dimensional space, which gives you a P1. And another P1 is produced by considering this vector. And so this is a P1 also because you have no conditions for the space at the first vertex. And the intersection is a one-dimensional sub-representation you can see on the picture. Yes, so if you can now consider the vectors corresponding to the red circled crosses, then this vector is these two vectors, they form a sub-representation of dimension 1, 1. And this is actually this intersection. So, so just to show you that these varieties are worth studying, so let me give you some properties. So they're not trivial at all. Theorem says that first of all, the xkn has n choose k irreducible components. So the second property is that each component is of dimension k times n minus k. And actually this xkn is a degeneration of the classical Grassmannian. So you can see that this variety has a kind of nice, interesting features. It is reducible, but the number of irreducible components is exactly all the characteristics of the Grassmannian, the number of T-fix points of the Grassmannian, whatever you like, and each component is of the same dimension. And this dimension is the dimension of the Grassmannian, well, actually, this xkn is a degeneration of the Grassmannian. So this is a kind of nice picture, and of course, to prove it, one has to work. But nevertheless, this shows that the varieties are interesting, and there are many other reasons why they are. So in order to somehow pass to the initial example, to motivation, to the Postnikov's Grassmannian, so let me introduce a bit of combinatorics.
Excuse me. Can you say about the intersection of the components?
Say it again?
Can you say something about the intersection of the components?
Well, how to say? So I don't have any concrete description. So how to say? I don't know if there is some nice structure for, well, describing the intersections, but probably one can try to do this, but I just don't know. The picture is somewhat complicated, so at least I don't know any easy answer.
Thank you.
Can I also ask, are the irreducible components, are they closures of orbits of the GLK to the N?
So yeah, this is a very good point. So actually, the variety, maybe I even would write it. Oops. So the fourth part, so XKN has cellular decomposition. And each cell is a closure of the automorphism group of the representation UN. So clearly, if you consider the automorphism group of the representation, so these are just the mappings between the spaces commuting with the maps of the representation itself, then this group does act on the Quiver Grassmannian, and actually each cell is a closure of this group. And there are some cells which are the large cells, and their closures are the irreducible components. And well, in particular, each cell is a closure of the out UN orbit. So this is really important for the study of these varieties, since the structure of this group automorphic group can be explicitly described, and then you can apply the group to the points and see what is happening.
Question.
Yeah.
Is it easier to describe projection spaces?
Could you repeat, please?
Is it easier to describe such degenerations of projective spaces?
So you mean the case k equals 1, yes? So let me give you again an example so you can see how it works. So example. Let k be 1 and is 3. Then the picture looks like the following. So we have 3 irreducible components. All components are 2-dimensional, and so we draw the picture, and then I'll explain what does it mean. So we have 2-dimensional thing here, and a 2-dimensional thing here, and 2-dimensional here. So there are three irreducible components. All of them are 2-dimensional. So I don't know if probably this picture has to be explained, but just want to say that there are 3 2-dimensional components, and they intersect, as you can see here, by 1-dimensional things.
Is it just coordinate planes and 3-dimensional space?
So you mean the irreducible components?
Yes.
So each irreducible component is a fibration of the following form. So there is a P1, and so here you have irreducible component, and the fiber is P1. And this is the general feature. There are exactly n for k equals 1. There are exactly n irreducible components, and each of them is a tower of P1 fibrations.
Mm-hmm.
So further questions? Okay, so now, so the combinatorics, as I said, so important thing is the notion of Grassmann necklace. So let me give a definition, and then I'll return back. But before, maybe even before the definition, so let me okay, let me give it. So so I take I, the collection I1 up to IN. So this is the definition due to Postnikov. And so this I1 IN with IA being a subset in the set 1 to n, and with the following properties, that the cardinality of IA is k for all A. This is the first thing. And the second thing is that IA sits in IA plus 1. So if we stop here, then this would mean that they are all equal because they have the same cardinality. But we also say that we can add here an A. So again, for each A. So meaning that the IA is a subset of IA plus 1, but if you have an A in IA, then this A does not have to be contained in IA plus 1. So an example of such a Grassmann necklace is again, let K be 1 and is 3. And I can take I to be just 1, 2, 3. So, well, you can see that all the conditions are satisfied. Yeah, by the way, A here from 1 to n. And for the last component, this means that IN plus 1 is just considered as I1. So for example, you can see here that the 3 indeed sits in I1 if you forget about this 3. So this is an obvious thing. Okay, and so before even, well, the connection with the UN representation is can be easily seen on the picture. So let me draw you the representation UN. For example, U3. And then you can see that there is indeed a connection. So let me, so U3 has 3-dimensional space at each vertex. And I just put a cross for a basis vector corresponding to vertex. And so now what are the maps? The maps for U3 are as follows. So we have this map, this map, this map, this map, and then here, and that's it. So, well, U3 is a representation of a cycle. The cycle contains 3 vertices, and therefore I need 3 vector spaces. So the dimensions of each vertex is 3, and let me put the numbers 1, 2, 3. Well, now, so this is the picture for the representation, and now let me somehow choose a vector at each vertex such that those vectors would be closed with respect to the maps. For example, I can choose here this 1, choose here this 2, choose this 3. So you can see that the maps annihilate all the circled vectors, and therefore this 1, 2, 3 is indeed a kind of, so if you choose the corresponding vectors, they form sub-representation of U3, or in other words, point in xkn. So we can put it as follows. So, well, an observation. Saying that the Grassmann necklaces label points in xkn such that at each vertex the corresponding subspace is a span of basis vectors. So actually, this is an analog of the n factorial or of the T fixed points in the Grassmannian for the classical Grassmannians of Leg varieties. And well, we can continue the cells forming xkn. So remember that xkn is the union of cells, and the cells are labeled by these Grassmann necklaces. So this combinatorial object somehow allows to describe the cellular decomposition, and you can say what's the dimensions of the cell in terms of these Grassmann necklaces and so on. So this is like the symmetric group governs the topology of the flag variety, and here the substitute is the set of Grassmann necklaces. Okay, so any questions at this point? Okay, so if not, so I have few minutes, and let me say something about the totally non-negative Grassmannians. Non-negative Grassmannians. So this is actually what, well, this is the reason why Postnikov got interested in the Grassmann necklaces and all this stuff. Let me first of all say that the field here is the field of real numbers, and the Grassmannians we consider are real Grassmannians, so over R, and it has the embedding, the Plucker embedding into the projective space of Verge kth Verge space of R to the n. So this is the Plucker embedding. Good. So now, what is the by definition the TNN Grassmannian? So this is the subset in GRKN consisting of the, yeah, maybe I should have said, sorry. Yeah, I should have said that. So the coordinates in lambda k of Rn are denoted by, say, xj. Where j is just the collection of numbers between y and n. So 1 less than I1 and ik less than n. So, well, because the basis in the Verge power is labeled by these objects. And then now I can say that this Postnikov's TNN Grassmannian consists of such points P such that J of P is non-negative. So of course, we have an embedding into the projective space. So this means that the points are considered up to the scalar. So you consider all the guys which have either non-positive coordinates or non-negative coordinates. So let me give you an example. So again, the simplest example is n being 2, k being 1. How does it work? So you have the Grassmannian 1, 2 is just P1, which consists of coordinates, say, A0, A1, which are not zero simultaneously. And then what is the GR 1, 2 plus? So you take the pairs such that they are both negative. How one can somehow describe this guy? So of course there are 2 points, first of all, corresponding to A0 being 0 or A1 being 0. And then if both guys are non-zero, then you have to add R plus, because you somehow divide by 0 and then you get 1 and the remaining thing is just R plus. So you can see that you have one-dimensional thing here and zero-dimensional things here. And let me get back to the X1, 2.
Before you, the question.
Yeah.
Is it always a closure of strict equalities? If you take strict equalities and positives, take a closure.
Yeah, that's right. Yeah. So actually, the claim would be that the general theorem says that you just fix some coordinates which are non-zero, and then this is your what is called cell or Postnikov cell. So of course you have to specify what are the possible subsets with non-zero coordinates, but still it's like yours. And so for X1, 2, you remember we had such a picture. And so here we have a decomposition into C and the point. And you see that this is somehow similar, but the dimensions are kind of reversed. So you have 2 one-dimensional things and 1 zero-dimensional thing. And in the TNN situation, you have 0, 0, 1. So, and in, so since I have only one remaining minute, let me say that it's a theorem by Postnikov saying that in general, the totally non-negative Grassmannian is the union over the set of Grassmann necklaces, Grassmann necklace Kn. So probably I didn't introduce this notation, but it's just the set of Grassmann necklaces of k-dimensional subsets. And so this is the R plus to some power, of course, depending on I. And the xkn has a similar decomposition. And we have C to the power K times N minus K minus C of I. So this is very similar, although you can see that the dimensions kind of are reversed. So the real topology of these T and N Grassmannians somehow corresponds to the complex topology of the Quiver Grassmannians, and this is the probably the last thing I wanted to say. So thank you very much.
Is there a way to dualize the top decomposition to get, like taking the dual graph in the planar case?
To dualize, say again, in what sense? So what do you want?
In the same sense as like in planar, for planar graphs, you can take a, I don't know the name, dual graph.
Dual.
And when you get dual graph, it's kind of switches the dimensions. Edges correspond to faces. Sorry, vertices correspond to faces. So is there any way to flip the dimensions?
Yeah, so there is some duality between Grassmannian Kn and N minus Kn, but here you have to change the dimensions. So I'm not sure this is what you want. But as for some other duality, I'm not sure. I don't know. So there is a duality which somehow sends IA to 1n minus IA. So this is possible. And then there's the change of the cardinalities, of course, and this gives you the duality. But I don't know if there is a duality inside each case separately, probably not.
What's the general context of these results? I mean, how far can you extend this? I mean, other dimensions, etc., other quivers.
Yeah. So, well, how to say? So these varieties, they XKN, they are their definition is very special for the quiver for the cycle. So I don't know if there is some kind of general object. However, the so I mean this is a kind of complex analog of the Postnikov-Grassmannian. However, this situation where you have a variety X and then you generate it to the variety Y such that the dimension is the same, but the number of irreducible components corresponds to the cells in X. So this context is rather general. So there are some papers by Drinfeld and maybe somebody else where they construct, Gaisgori maybe construct such a picture, but their construction is a bit different from what we do, and probably some general picture of this sort can be done for other quivers. However, at the moment we don't know, but this is possible.
Is there some role of Postnikov networks in work of Quiver Grassmann? Because if I'm not mistaken, Grassmann networks label matroid cells when Postnikov networks label just elements of matroid cells. So is some similar construction in Quiver Grassmann?
So this I don't know. So from the point of Quiver Grassmannians, these Grassmann necklaces, indeed, they label the cells of the cellular decomposition. Well, I don't know if there's some extra data here. So far, at least, the only thing we need is those Grassmann necklaces and not anything else. But but maybe. So it is, I don't know.
Question. So what happens if you just replace the complex theory of quivers by the real one?
It's okay. It's absolutely possible. So I mean, for the Quiver Grassmannians, you can work with the real numbers instead of complex numbers with no harm. So this just would mean that the cells are going to be not complex cells but real cells. Otherwise, the structure of the variety is absolutely the same. So it's not sensitive to the change of the field.
And is the results in space in the second row with R, when you replace C with R, is it homotopically equivalent to the top row?
I don't think so. Well, to say the truth, I don't know, but no, I don't know.
No, definitely not. So you get, instead of two spheres, you get two circles, for example.
So let's see if indeed if k is 1, yes, and n is 2, then what we do have are you're right. So we have these two guys, yes, here, and for Postnikov's thing we have so we have this P1 plus for Postnikov. So so for in his case, these are just R plus and 2 points. So probably not.
Any further questions? If not, let us send the speaker again.
So thank you very much.
The next talk will not be available by Zoom, but the talk at 4 will again be available. So join us.
Thank you. Bye-bye.